basic concept, and she just kept saying, we like that part.
Sounds good.
Yeah, I don't know. I didn't actually watch the audio.
She's saying all.
She's saying along to it.
Yo, Alex, are you gonna put Mark's haiku up on the board? You said you would.
Yeah.
I said I would put my favorite one up on the board.
No, you said you put Mark's up on the board.
I thought
it was like pending approval.
it was pending approval. I think my picture was. Oh, I get to put the second one up, right?
Okay, fair enough. You can put either one up if you want, I guess. I think you should put the first one up, though.
Oh man. There are a lot of people who. There are a lot of people who will watch this and wonder what I'm doing.
Are we recording right now? You can put
Yeah,
it out
we're
of frame.
Because if they have watched it followed the course, it will make sense. It's a reference to a previous episode.
Yeah, right?
Yeah, so
Previously
because Mark was one of the people that sang in the previous video where this reference is drawn from, I'll write his haiku. I swear there are people in the world who are going to be like, that's cool of mine's doing that. They're just gutter mouth. Think of your... And you capitalized it, that's what it's Whenever life gets you down. For those whenever life gets you down. I feel like I should explain this to people who watch this for the first time. But there you go. Oh, you guys are going to sing it.
Yeah, Mark, why don't you
Okay, so now I wrote it, and now I'm going to erase it.
You can sing it as a class.
Now, you can watch the video from the Valentine's Day lecture where that all happened. Okay, so anyway.
Can this lecture be
So,
put up the Valentine's Day lecture on the board and just watch it?
so since we're talking about big things, let's talk about the biggest thing, infinity. Okay, so I know that last time many of you kind of walked out feeling like I had just beaten you over the head with a big infinity stone, and today we're going to continue that discussion. I'll kind of recap sort of the general story. Hey, Ariel, be the good student, pay attention. Don't make me call you out. I'll put your card on top and leave it there. But we're going to start by kind of having a broad stroke view of what we did last time, because last time we really got into the weeds with expressions, and those are never the most inspiring thing to see. But we're going to start with broad strokes, and then we're going to see a few more details, but really where this story eventually leads, because the modern place where we are in understanding these infinities is very, very different than where people were when they started discovering them and handling them 50, 60 years ago. So we know that if we calculated amplitude m in quantum field theory, usually we write down all the elements following the Feynman rules for whatever interaction we're dealing with whatever matter we're dealing with. And we know that there's going to be integrals over internal momenta, but there's also going to be delta functions for every vertex, and we can use those delta functions to do a lot of the integrals trivially. But at the end of the day, we're going to be left with an overall delta function that conserves the total momentum coming into the process and the total momentum coming out. So we're always going to end up with this, and then we know the last step in the Feynman rules is we erase this and we multiply by I to get m. But anyway, and then we are, in many cases, and we saw some examples last time, we're going to be left with an integral over, and this should actually be a product over k, d4qk over 2 pi to the fourth. And what I have in mind here is that these are going to be the q's that I could not do the integrals for with the delta functions. So for example, if we just have a simple tree level diagram, we have a q here, but we have two delta functions, and we can use one of them to do the integral over q, and so there's no integral over q left. However, when we looked at this diagram, we get 1, 2, 3, 4 delta functions, but we get, we have too many internal momenta, so even when we use all the delta functions, there's still an integral over momentum left. And it's these leftover integrals that tend to give us problems, because these are normally running from 0 to infinity in magnitude, and when you integrate to infinity, usually you can get issues. Not always, but usually. Okay, so generically, the procedure, so these things usually diverge. And the procedure which we saw in detail last time, I'll kind of play out in broad strokes. So if you just think about it, like regardless of the sort of details, one way that you could kind of try to cure this, that is regularize it, which means to make it finite. One way you can do it, which is not exactly what we did last time, is by just inserting the number 1 in a very interesting way. Let's give me the squared. Okay, so what I have in mind here is that this quantity is if m twiddle goes to infinity, then what is this quantity? M twiddle going to infinity meaning it's much larger than qk squared. It's 1, right? So there's a sense in which if I stuck this into this integral and I said I'm going to take the limit that m twiddle goes to infinity, I actually haven't done anything to the integral because I've just stuck in a number 1. Okay? But then if we back off of that and we say I'm actually not going to take m twiddle to infinity, then the effect in the integral is that we've increased the power of q in the denominator. And if we have enough factors like this, a lot of times we can take a divergent integral and we can render it finite. Because we know if we keep increasing the power in the denominator, eventually we'll get to an integral that's finite. Okay? So this is what's called Polyvalars regularization. And you sort of are coupling the theory to some fictitious new massive state. But it's fictitious. At the end of the day, you're going to take the mass of that thing to infinity. That will restore the divergence, okay? But that's okay because the true answer is divergent. So let me remind you of the words we used last time. So we have an amplitude, m, it's divergent. The first step in renormalization is to regularize it, which means rewriting it so that it would be finite. We did that last time by saying instead of integrating to infinity, you integrate up to some cutoff. That did the same thing, okay? Now what's important is really the next step. So if we regularize the theory and we're lucky, then what we'll find is that that we'll have m, and it will kind of break into 2 parts. One part will depend on this parameter m twiddle, which we sort of fictitiously introduced. And then we'll have another part, say m prime, and the second part will not depend on this. Okay? And if we're really lucky, what we'll find is that when we take m twiddle back to infinity, this will diverge, but this will remain finite. Okay, so we're kind of taking the thing which is overall infinite, and we're in a meaningful way breaking it up into a finite piece and a divergent piece. Yes, Spencer?
So why are you treating the fictitious thing as some sort of mass as opposed to...
That's just one mechanism. There's many different mechanisms. So last time we just talked about a momentum cutoff. You could also do dimensional regularization where you formulate it in a different number of dimensions, and then in many cases in a different number of dimensions things actually are rendered finite, and then you take and then restoring it is taking the limit that d goes back to 4. Yeah.
So I'm not sure if you had answered this, but do these infinities arise just because we don't have the math?
No, that's what we're gonna talk about today is why are these infinities arising.
Right. So,
And we're gonna have a much more comfortable understanding of them in a bit, okay? So all right, so does everybody kind of remember us doing this last time? We took the m and we broke it up into a sum of 2 things, one of which we said, well, that's infinity, and the other one is finite, okay? And by the way, this whole procedure, if any of you have ever seen this funny expression, it's sum over n of n? Yeah, sum over n of n.
It's like minus 12.
It's minus a 12. Okay, that is exactly this. Okay, the whole point of this expression is that this is, of course, infinity, But you can regularize this infinite thing to provide a meaningful finite piece, and then of course a divergent piece. And the value of that, if you've never seen this, the value of that is you can then start making meaningful expressions like this. Because after all, these are both infinite, but is there a sense in which there's an infinite piece from here that subtracts an infinite piece from here that's 0, and then there might be some finite thing that's left over that gives me a non-zero answer. So that's why regularization is important in these purely mathematical contexts. It gives us sort of a way to differentiate between different infinities. Okay? Well, that's exactly what we're doing here in this quantum field theory context, or particle physics context, I should say. But anyway, okay. So we saw this last time, and then the really important step of renormalization is if we're really, really lucky, then the M-dependent parts, then the parts which actually depend on M, look like the following. They look like an expression of some form, but in that expression, we have our coupling constants split into two pieces. And this split, and I'll put letters on it to make connection with what I talked about last time. So the split is as follows. This guy right here is the quantity that we say we actually physically measure. That's the physical value of the coupling. So we talked about if we go and measure the electric charge in an experiment, that would correspond to this quantity. This it would correspond to the quantity that we had originally started formulating our theory with, the fundamental value of the electron charge, for example, or the electric coupling, which we call the bare value. And then this is typically, if we're lucky, where we find this divergence manifesting itself in the form of M. Okay? And then we made this really huge step. We said, the fact that this is infinity is actually okay because we literally have no access to this quantity. Okay? So the fact that this thing is diverging could potentially be canceled by the fact that the bare value is divergent. We don't know. The only thing we really care about is this finite measured value. So what we can do is we can rewrite our theory in terms of this alone, and then we don't have any infinities to worry about. The problem arises when you try to say, I'm going to formulate my theory in terms of this quantity. Because you literally have no access to what you should be putting in for that value. All right? Now, we didn't see this next piece in the example we did last time, but in a lot of situations, the same thing can happen with masses in the theory, and that is that you can have a mass term which has some contribution that diverges. So we could talk about like the mass of the electron. And in certain situations, and I'll show you one in just a minute, you'll find that so from this we said that the coupling varies with energy scale, and then there's a divergence we have to handle. We can also discover through analyzing certain diagrams that the masses of things change with energy scale. We can get divergences in the masses of things, and then we make the same statement. We say, well, I actually don't know what the fundamental physical mass, or the fundamental bare mass of these fields are. All I know is what I measure. But what I measure is typically a large distance. So the fact that this diverges, it's fine, because this could just do whatever it needs to do to soak that up to make this finite. Okay? If this miracle happens, and there's no guarantee that that will happen, that it will split up like this. If this miracle happens, then what you're able to do is you're able to rewrite your theory in terms of a finite number of finite parameters. So there's, in this case, there might be one coupling and one mass. Okay, and by these, just two redefinitions, I've removed all the infinities from the theory. If you can do that, then the theory that you're working with is called renormalizable. all right? If you can't do this, then the theory is non-renormalizable. If you can't do this, then there is no way to blame infinities that you're seeing on parameters that you really don't fundamentally have access to. And that could just be because you have more infinities than you have parameters in the expression to begin with. Like if you've got 12 infinities, but there's only like 2 masses and 1 charged, you're screwed. Okay, so there's just kind of a balance. Like, can you explain every infinity by some parameter in the Lagrangian that leads to the expression for n that you're dealing with? Okay, Jacob?
Do we consider then non-renormalizable theories as non-physical?
Well, we're going to get there. That's going to be the theme of today, is making sense of this. Okay. So there was certainly, in the very early days, there was an idea, a conviction, and this has changed, but in the early days there was a conviction that we should really only be considering renormalizable field theories. Because if a theory is non-renormalizable, it's simply sick, and there's just no way to make sense of it. Okay? And the good news is that at Hooft proved that the standard model, as we've been studying it, is renormalizable. Okay, the SU3 cross SU2 cross U1 with all of the matter content of the standard model. It's actually a renormalizable theory. Okay? So it seemed like we were in good shape. The problem is, if you, on the other hand, try to do perturbative quantum gravity, that is, you take gravity, so you take something like Einstein's general relativity, but you do exactly the same kind of thing you do with Feynman calculus. So you kind of take a approximately flat geometry and you just treat like small fluctuations in the geometry. And then you do perturbation theory with that. And there's a way to write this as a gauge theory. So there's a lot of nice similarities to what we've been talking about in particle physics. But if you do the same game with perturbative quantum gravity, then this is not renormalizable. Okay? And this, for a long time, was deemed one of the fundamental sicknesses of gravity, was that there was no consistent quantum theory because it was non-renormalizable. Okay? And it's still non-renormalizable. That hasn't changed. But our appreciation of why it's non-renormalizable has shifted quite a bit since then. And I'm going to tell you about that shift. Okay? So, a couple of details before I kind of get into the eventualities of how this story finished. So the first thing I'm going to do is I'm going to give you a little bit more of the story of renormalization in quantum electrodynamics, which is the example we talked about last time with some detail. And then we're going to talk a little bit about how renormalization plays out in the quantum chromodynamic story, because there's actually a very interesting observation there that feeds back into some of what we did this semester. And then I'll kind of end with the more modern interpretation of how all this works. So in QED, last time, and I'm not going to write down all those big nasty expressions, we considered at lowest order to electron muon scattering, for example. And remember, just as a detail, because I hope you don't forget these things, it's easier to consider electron muon scattering because you don't have to add in a second diagram where you just switch the 2 outgoing things, because a muon is distinct from an electron. If you do electron-to-electron scattering at the leading order, you have to include a second diagram where these 2 are switched. So that's the reason I keep picking on electron muon scattering. It's only got one tree-level diagram. And then we considered a correction to that at 4th order, where we just had some virtual electron-anti-electron bubble pop out from the intermediate photon. And this is, of course, where we got all of our divergence love, and we did all our renormalization and so forth. And what we found is that this led to renormalization of the electric coupling. That's all we had to deal with last time, was the electric coupling. Okay, so all the expressions we worked with were focused. What is going on back there?
Jonathan almost died. Sucked water into his
You gonna make it?
Oh, yeah.
All right. The rollerbladeless man can't drink, can't swallow. All right, so what we discovered last time in the technical details was that we could handle the infinity that arose here just by appropriately redefining the GE. Basically, this is the electric charge. Okay, it's E times some fundamental constants. However, this is not the only fourth order diagram. There are quite a few more, and if we just draw what the other fourth order diagrams look like for this process, we find the following, and there's sort of a pattern that quickly emerges. All this whispering like, I can't hear you. You guys are so whack. Okay. Shh. And there are others. So notice they're all fourth order. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And you could also do diagrams where you have a little loop here and a little loop here, and you could do a little loop here. Okay. All right. Now in all these are the electrons and these are the muons. All right. So if you actually start exploring these diagrams and write down their contribution to M, you find divergences for the first three. Okay, these are actually finite, so they don't play a role in the renormalization story, it turns out. But these first three do, but they have an interesting interpretation. So these diagrams renormalize the mass of the electron. If you think about it, this little photon loop really doesn't care about the rest of this diagram. It doesn't even care about the fact that there's a muon there. It really only cares about the fact that there's an electron flying through space. Not flipping through, electrons don't flip, they fly through space. So the electron flying through space, then it burps out a photon and then swallows it again. Okay? That can happen. All right? And what this is doing is this is contributing non-trivially to the self-energy of the electron. But that's caught up with basically the rest mass of the electron because everything else is just kinematics. You can shift your reference frame and change that. So what we find is that when we consider these diagrams, we get infinities, but we can cure those infinities by carefully redefining the electron mass. Okay, in the same way that in this story we were able to cure this infinity by redefining the electron charge. This diagram is a vertex correction, and you can kind of see that. It's kind of taking the basic vertex and it's kind of making it more complicated, and it renormalizes the electron magnetic moment, actually. Okay, so the point I'm trying to get at is that there's a lot of different parameters that come into the story, and we can encounter many different divergences, and many of these divergences can be associated with certain parameters. And if we're lucky, and of course we are because we know QED is renormalizable, then we have enough parameters to tweak to accommodate all these infinities. Nathan?
Yeah, so you can only renormalize, redefine the electron mass. What about the muon mass?
Well, that's what I was about to say. So if I included the diagrams with these loops, those infinities which would arise would be renormalizing the muon mass. Okay? So yeah, so everything I'm saying for the electron also goes for the muon. Okay? And in particular, this is the electron vertex correction. If I did it here, that would be the muon vertex correction. Okay? Yeah.
So for the non-divergent diagrams, when we calculate those amplitudes, do we have to use the renormalized coupling or whatever in those expressions? Like, because we're going to have like GE squareds and stuff in those finite diagrams. Are those correct values to use now?
Yeah, well, well, this would be part of the total story. So unfortunately, the total story here is going to be way more complicated than what we talked about last time, because you've got many parameters that you're trying to tweak at once. But remember, the whole idea is to take all of these together and effectively write some new kind of expression for M with all of these redefined parameters that calculates the whole answer using a single diagram of this form. So yes, even though these aren't divergent, they're going to play a part in the overall redefinition so that we can reduce it to this one effective diagram. So they'll play a non-trivial role in the renormalization. Remember, renormalization had two facets that were of importance. One was you got these infinities you had to figure out what to do with. But the other one was just the observation that infinities aside, the values of couplings tend to change with energy scale they run. And so too do masses and all the other parameters. And so these can play a role in that running, even if they're finite. Did that even come close to addressing the question you asked?
I suppose. I mean, so like in this new renormalized setting, we're not taking sums of all these different levels of like perturbations. We're just saying, you know, like we put a physically measurable quantity in one diagram instead of taking a sum of a whole bunch of stuff. Is that what you're saying? Like we formulate the new theory just in terms of measurable quantities, and we're not concerned with taking higher order perturbations.
Okay, yeah. So maybe I should say the following: if you're going to do anything at fourth order, you should do everything at fourth order. There's no sense in considering this and then ignoring anything else at fourth order, because those are all similar orders of magnitude. But if you do everything at fourth order, and you go and you do the renormalization, there's a certain sense in which you can ignore higher order just because they tend to be less important. So the idea is you would write down an M for all of these diagrams, you'd take that entire expression and you would find a way to collapse it into a new form that looks like there's just this, it's coming from this single diagram.
So that single diagram is now a fourth order estimate. It's not the...
Yes, and there is a sense in which where I'm going to go with all this will make sense of that. Why suddenly things can kind of go from looking simple to looking complicated. And we're going to get to that in a few minutes. Matt.
So this might be answered in the next couple minutes, but if we go to like sixth order here.
Jesus.
No.
Yeah, you go there.
And we want to renormalize the mass of the electron. Will it be the same renormalization as the fourth order, or will it be different somehow?
No, it would be different, and I'm actually going to give you the exact answer for at least one case in a minute. So, no, every time you go further out, bye Kowalski, you're missing the best part.
I know, it's really sad, I can't
I don't know why, it's like a scheduled class.
Yeah, I have to, I'm performing in a art thing.
Good luck, dude.
It's good though, it's good fun.
You just want to be on camera.
Get back in your art thing. All right. So what? Yeah. Oh, okay. So now I said all that, and then I actually have to go back and be a little bit more honest. So I said all that, and the truth is that. And it turns out that for QED in particular, the contributions of these three diagrams actually all cancel. So it turns out that in QED, you really only have to worry about the divergences appearing here. Okay? But that's just a special case of QED at fourth order, and for other forces or at higher order, generally speaking, a lot of diagrams are going to play a non-trivial role. But there is an interesting observation for this, the fortune of this cancellation, and that is that so this diagram renormalizes the vertex, sorry, if these did not cancel, then you would have to combine these diagrams with this diagram to try and render the entire thing finite. But the problem is that these diagrams are renormalizing the masses of things, and this is renormalizing the charge. So what we would find is that if all of these things were playing a non-trivial role, the renormalization of the electron charge would be different if we were doing it for a muon versus an electron. So that would actually mean that the electron and muon charges would be different because they would run differently with energy scale. Because the electron and muon have different mass. So you don't want the renormalization of the mass to sort of be a part of the renormalization of the charge, because it would violate our experimental evidence that even though the electron and muon have different masses, they seem to have exactly the same electric charge at any energy scale. Okay, so that happens. Okay, so it's not, it's just, it's good that it does happen, otherwise we'd be screwed. Okay, so what I want to talk about now is renormalization in QCD. And in QCD, we're going to this is going to lead us to an interesting conclusion. So remember, in the QED case, we found that the contribution from this diagram eventually led us to an expression of the following form, and I'm going to write this down. It's going to be in a slightly different notation than we talked about last time.
Oh man, it's 191 squared.
I have no idea what y'all are talking about, but
I can't fucking read.
You can read, just go.
so that alpha is a new symbol, where GE, so this is the electric coupling, GE, the coupling GE is just 4 pi alpha E. Okay, and if you, all of these things are related. And then you can also write GE as, I think, E times the square root of 4 pi over H bar C. But anyway, so last time we worked in terms of GE. This time we're going to work in terms of alpha because it makes it a little more direct comparison to QCD. But anyway, and this is the expression that we got. And here we're considering momentum transfers. This is a simplified version where the momentum transfer is actually larger than the quantity, the mass of the electron squared times c squared. And what's interesting is that in QED, so to Matt's question, if you took into account higher order diagrams, then you can actually do the sum explicitly. Because if you keep inserting bubbles, and you keep writing down the terms in M, it turns out that it's just a geometric series, which you can sum. Now this is only if you're including just additional bubbles. If you start including higher order diagrams that have like vertex factor corrections and self-energy corrections, then it doesn't simplify like that. But at each order, just like what we found at fourth order, these are the dominant contributions. Okay? And so if you actually sum all of these, then you find the expression for how alpha runs with Q is slightly different. Okay. Okay, so what? Either way, it doesn't really matter, but either way, so Matt, to answer your question, as you go to higher and higher orders, the form of the renormalization changes. Clearly, it's different if you go to infinite order than if you go to fourth order. But in either case, even if you stop at fourth order or go to infinite order, what happens to the coupling alpha as you go to high momentum Q, or Q squared, high momentum magnitude Q squared? So in these expressions, alpha 0 is what? But what number is it? Say it again?
It is the 1 over 137.
Which we get from? Yeah, it is the measured value of the coupling, where the measured value is proxy for large distance. Okay? And it's 1 over 137. So this is a constant. Clearly 3 pi is a constant. In this context, we're treating the mass of the electron as a constant. We have to be a little bit careful about how we deal with these expressions. But in this scenario, if Q increases, what happens to the denominator?
It's big.
Or the denominator gets big, so the overall expression gets small. Right?
Other way around.
So,
Yeah.
Jesus, right?
Art is the house.
Natural art keeps.
So in I think I might have my inequality backwards. I want alpha to grow with increasing Q.
It doesn't. Right now, because that log gets bigger than the 1 minus that thing,
Gets more negative.
gets smaller.
But the question is it negative or is it smaller, positive? I know at fourth order it's obvious. But somehow I should be able to rationalize this for the complete sum, and I don't, off the top of my head, see why. So I'm just gonna punt. I'm just gonna punt.
Nice.
Alpha Q squared should be increasing. Yeah, no, we're being silly. So, no. Obviously, it starts increasing, but then you hit a divergence when the denominator goes to 0. Okay? And then it starts decreasing once you go past that divergence. But that's not really helpful. Fortunately, if you actually look at the energy scale at which this divergence occurs, it's about 10 to the 280 MeV. So it's not really an energy scale we're worried about in the natural world. Okay? But the point is for energy ranges that are small compared to 10 to the 280 eV, the electromagnetic coupling, the renormalized electromagnetic coupling is increasing, and the important observation from that is that this implies that the effect of these virtual particles is that they're screening the electric charge, right? Because remember, what's the picture? You've got this muon sitting there and you're slamming it with an electron, and the more Q you give the electron, the closer it gets, but the closer it gets, the more of the fundamental charge it's seeing. It's less screened. And so you would expect that for screening, as you go away or as you probe, at distances that are less than, as your probing distance gets larger, as your closest approach distance gets larger, you should see less net charge if there's screening occurring. Okay. So if you turn that around, if the closer you get, the larger the charge you see, that implies that there's screening. Okay. Now in QCD, what we find is the following. So in QED, that's all there was screening. In QCD, we of course have a diagram that looks a lot like this. So we have a quark-quark scattering via the exchange of a gluon. And then we can have a correction to that that's exactly of the form as we considered in QED. Okay, we just have some virtual particle-antiparticle pair. In this case, it would be a quark and an antiquark. Okay. And you can actually do the analysis here and discover that, in fact, once again, the QCD coupling alpha S grows with Q squared. And so, at least for this contribution, that again leads to screening. All right? However, this is not the only type of diagrams in QCD. Yeah, Will.
How do we, because in the other cases we say that the 0 parameters, the long range, but how do we talk about that for the strong force? Because it gets stronger over
Well, no. Let me just finish the QCD story, and then that's the butt of the whole. Yes. Okay. So remember in QED we had a lot of other diagrams we drew at fourth order, but they all dealt with fixing up the self energies or the vertex. As far as doing stuff to the photon itself, the only thing we could do was just insert a bubble. Okay? However, in QCD we have extra vertices, right? What other vertices do we have in QCD that we don't have in QED?
Gluon.
We have gluon vertices. And so it turns out that we can start looking at diagrams that look like this. Okay? You guys are loving this. So these are all allowed vertices in QED. So there's a 3 gluon vertex and there's a 4 gluon vertex. Okay? Now, and there are others, but if you actually start calculating the contributions from these, which we're clearly not going to do because I wasn't even willing to write down the vertex factors associated with these, remember? Somebody wrote a haiku about it. You'll discover that these actually lead to anti-screening. So if you just look at these diagrams, what you discover is that alpha S Q squared decreases with increasing Q squared. So we have two competing effects. We have from these contributions screening, and then we have from these contributions anti-screening, but of course they're both present in the theory. Okay? So the question is, which one wins? Do they cancel? If they canceled, that'd be cool. Nothing would run. There'd be no infinities. Okay? Well, what's interesting is that so there are two numbers that turn out to be very important if you're trying to figure out what's the net effect of this. The first one is the number of quark flavors. So how many quark flavors do we have? Quark flavors.
191 stars.
Oh, no.
So that's a different quark name. So 6, the up, down, top, bottom, strange term. Okay. So there's the number of quark flavors, and I'm actually just going to write this as F for now, and we'll come back to the actual number in a minute. So the number of quark flavors are going to directly impact the screening part, because for every different kind of quark, I can put a different bubble in here. So I could do a bubble of up, up, down. And then I would do a second diagram with a down, down, anti-down, and then a charmed, anti-charmed, and strange. And I have to include all of those contributions. So the more quark flavors I have, the more of these diagrams I'm going to have to include, which means that the screening effect grows. Okay? It's also going to be important to know how many gluons there are. Okay, and the gluons are going to be a proxy for, do I have this written down?
It's a fiesta.
No, actually, sorry, number of colors. Did somebody else leave? Oh, you came back, sorry. Okay, so the other thing that's going to impact this is the number of colors. What is the number of colors going to impact? So how many colors do we have? We have 3. Okay, and I'm just going to write this as n. But we have 3. What does the number 3 determine in the QCD story?
What do you mean?
So what does the number 3 determine for us, among other things? It determines the number of gluons, because gluons are bicolored. The more colors you had in your theory, the more gluons you would have. Okay, that's obviously going to contribute to the number of anti-screening diagrams, because these are different just by different gluons. The more individual, come on, you guys. Spencer, get over there. I don't know what y'all are doing, but you can go party after class is over. I'm going to make this last another 2 hours. You guys don't get on board. It's like 3-year-olds. But what else does the number of colors impact? Yes, it impacts the number of types of quarks because a red up quark is different than a blue up quark. Okay? Remember, these colors are not values, they're actually different kinds of charge. Okay? So at the end of the day, you're going to get a different degree of screening and anti-screening depending on these two numbers. And the exact dependence is a little intricate, but in the end, what we find is that you can boil it down to this combination, 11 times n minus 2f. And if you take this number and you calculate it and find that it's greater than 0, then anti-screening wins. And if it's less than 0, then screening wins. That is, if you take all of these diagrams into account, if the number of colors times 11 minus 2 times the number of flavors, if this number is greater than 0, then these diagrams are going to dominate. And in the alternative case, these diagrams are going to dominate.
Why is it only a numbers game? Like, why doesn't the mass of the quarks play into it? Like, why do we assume like each thing is equally favorable?
Because the map, so what do you mean by?
Well, like, I guess it's the equivalent of like a thermodynamics. Like, each microstate is equally as probable. It seems like we're kind of making the same.
These are not on shell. So these are virtual particles. They don't have to satisfy the mass-energy relation that we're used to. So there's a lot of flexibility in these internal diagrams that we don't have to, that we would normally be more concerned about if these were actually real particles, but they're not.
Is there any way of recovering 0 from that equation?
Well, you tell me.
Equal to 0? I don't think so.
Well, wait, so I don't want to get too hung up on this. What's the answer?
Greater than 0.
Say it again? What's the answer for the standard model?
21.
Positive. 33.
So n is what for the standard model?
Positive.
3.
Yes.
N is 3, F is
6.
6. So what do we have?
21.
Woo! Positive.
Yeah. Anti-screening win.
So anti-screening is going to win. So if you think about it, this is weird. It's exactly backwards from QED. The net effect is that if we throw quarks together at very high energy, their coupling is getting smaller and smaller and smaller, which means at very high energies, if in fact let's just take it to infinity, or let's just take it to a really, really high energy, at high energies, quarks are non-interacting. This is exactly why when we were doing calculations for, say, mesons, which is a combination of a quark and an antiquark, and we drew diagrams and treated them like a scattering process, we could treat these like they were basically free quarks. Remember, this whole Feynman calculus depends on the particles coming in and the particles coming out being effectively free. And then you're treating the interaction between them perturbatively. Well, if these two things are bound up in a meson, how are we ever allowed to treat them as free? Well, it is exactly because QCD is asymptotically free. At high energies, it's a non-interacting theory. Okay, inside of baryons, inside of mesons, the quarks in there are barely interacting with each other. It's exactly the opposite of what you think of when you think of electromagnetism. Now, you could be tempted to turn this argument around and say, okay, if the interaction or the charge or the coupling is going to 0 at high energies, then what would it do at low energies? It would get large, maybe go to infinity. Well, that would correspond to taking two quarks, which are at a very small distance, i.e. high energy, and separating them to a very large distance. But what do we know you can't do? You can't do that. And so what you might be tempted to say is that you just proved that this can't happen. Because the further you separate the quarks, the larger the coupling gets. But the larger the coupling gets, the harder they are to pull apart. And then, as I mentioned earlier, you model this as a flux tube, blah, blah, blah. So one might think that you've just proved confinement. You've just proved that you can't get quark bound states separated because the coupling grows as you pull them apart. But we didn't prove it at all. Why? And trust me, if we did, we would we'd be famous. What's wrong with extrapolating this to try and say, I've proven confinement?
You just have to pull harder as you increase their separation.
Well, that's the intuitive way of thinking about it.
It's like
if the coupling is, it's like a rubber band. It's like a tensionful object. It pulls back harder the further you pull it apart. So it makes sense, but there's something in this argument that is a flaw.
If your coupling gets bigger than 1, your perturbation is no longer valid.
Exactly. Everything that we just described was based on perturbation theory. And when you pull these things far enough apart that the coupling is bigger than 1, none of your perturbative calculations count. Okay? So you actually, to talk about exactly what's happening between a quark and an antiquark at a separation where the coupling is getting order 1, you have to use non-perturbative methods. You can't use perturbation theory. Okay? So this is suggestive, but the problem of quark confinement is by no means resolved. All right? Okay, so are there any questions about the QCD part of this story? Because I really want to move on to the interesting part. Okay, so now we're going to get to where this all actually really sort of gets an explanation. I wonder if they thought to just see if there might be classes going on
No way.
during their Cinco de Mayo.
From the 3rd of May.
Their Cinco de Mayo, 3rd of May morning.
It's fine, right?
Okay, so what I'm going to do now is, in order to give this all sort of an interpretation, okay, and to kind of segue into our modern understanding of this story, I'm going to give you a little bit of a historical anecdote, okay? So way back in the day, before we actually had the weak interactions as we know them now, based on an SU2 invariance, and the strong interactions based on an SU3 invariance, Fermi was trying to write down some kind of model of beta decay. And so what he discovered was that he could sort of explain beta decay in a field theory context if he included matter fields. Now he's doing a field theory, but he has a proton field, a neutron field, an electron field, and an electron neutrino field. And then he has an interaction vertex defining the sort of fundamental interaction in his theory, which looks like the following. Okay? This is called the Fermi 4-point interaction. Okay? And you can take this fundamental vertex, and remember the rules of vertices. You can take them and twist them and kind of wiggle the arms around and do whatever you want as long as it's got that vertex. Well, this vertex immediately describes beta decay because you can take it and do this. And then we've got the neutron decaying into the proton, the electron, and the anti-electron neutrino. Sorry, that arrow should go backwards. Okay? And so using this field theory, you can calculate the amplitude for this process, and you get a number. And early on, it was a pretty reasonable comparison to experiment. Now, eventually, this was proven to be wrong. Okay, it wasn't quite accurate. by experimental observation. Like we eventually, we got to high enough energies that we actually could see that there was more to this story than just this, and I'll show you the remainder of the story in a minute. But what's really interesting is that the theory that Fermi wrote down was theoretically telling him that it wasn't right. It was theoretically telling him it wasn't right because it was non-renormalizable. It was saying, in this theory, there's this thing that's going to infinity, and if you allow Q's to go all the way to infinity, your amplitudes M are going to diverge. But you've got no justifiable reason, because you can't do the whole renormalization story. That's what a non-renormalizable theory means. It means you don't have enough parameters to tweak to explain the infinities. Okay? So, theoretically, this theory was saying, hey, you know what, I'm sick. But we know now why it was sick. In truth, what's going on in this picture is something like the following. Oh, it's so awesome.
Aren't there downs in a proton?
Say it again?
Aren't there downs in a proton?
Yeah.
You went above
Downs
us.
in a neutron.
Oh, sorry. This should be up, down, down. And up, and I'm going to put the down there. There we go. Thank you. Okay. All right, so notice, this is our current understanding of this process. Okay? Definitely more complicated than what Fermi wrote down. All right? If you write down the amplitude for this, you'll find you'll have a U bar for the neutron, some gamma factors, a U factor for the proton, and then the all-important weak propagator. And then another spinner sandwich. And there's some other factors in there that I'm leaving out there, not that important. Okay? And we recognize the structure of this, right? This is a spinner sandwich that kind of arrives from a vertex. We've got some vertex, we've got the ingoing and the outgoing things. And then this is the propagator of the internal W. So we've got some propagator, and then we've got another spinner sandwich that corresponds to this other vertex. Okay? But now what I want you to do is the following. You ready? Look at the diagram, look at the expression, and then squint your eyes. Let's do this. That's good, Brooks. Like, are you in a drama club or something? It's like, oh, that's a stage direction. Squint! Okay, so squint your eyes. What happens?
Can't read anything anymore.
Okay, no, by squinting your eyes, what I mean is, when did this break? When does this break? This breaks when Q gets too big, right? Okay, that's typically where non-renormalizable theories go cray-cray, is when the Q gets big. So let's take this story and let's look at it when Q is small. In fact, let's look at it when Q is much, much less than MWC. If we do that, then M just becomes U bar N gamma mu 1 minus gamma 5 UP minus, actually, just eta mu nu over MW squared C squared. Okay? All that changed was that this propagator factor simplified, and you've used this simplification in your homework. Okay? But this is really just a number. This is not doing anything interesting structurally to the amplitude. So there is a reasonable sense in which this expression is becoming not much more than a vertex factor times a vertex factor. And what I mean by squinting is that you're essentially ignoring the W, and you're bringing these two things so close together that you never even realized that there was a W in the picture. Here, the two vertices are obviously separated by this propagation of W, but in this version, the propagation of the W has been sort of thrown out. And so you have the two vertices immediately appended to each other. And so you have this sort of two vertex, or basically four vertex interaction. Okay? So what's the lesson here? Well, the lesson here is the following. If we write down a non-renormalizable theory, it's not that it's physically meaningless. What it means is that, especially if we find that it actually describes something in nature, because this was describing, pretty accurately beta decay, at least at low energies. But if it's non-renormalizable, what you expect is that if you go to high enough energy, the theory needs to be replaced by a more fundamental description. The more fundamental description is typically called the ultraviolet completion of the theory. Ultraviolet being high energy. So at some scale in the ultraviolet, high energy, you have to replace your effective theory by a more valid, more fundamental theory. And the expectation is that if you have a good ultraviolet completion, then the ultraviolet completion itself would be either renormalizable, that is, you could just take the momentum all the way to infinity, or better still, it'd just be finite, where you don't even have to mess with renormalization, because there are just no infinities in the theory. Okay? So in the 70s, Ken Wilson came along, and he really formalized this idea. Okay, he said that essentially what you're doing with renormalization is, or in the context of non-renormalizable theories, is you're basically hitting an energy speed limit. And that speed limit is the validity of the description you're using. And beyond that, you need something better, something more fundamental. But he said you could turn that around. So you can turn it around and say, I don't know why I just erased that. There you go. You could start with a fundamental description. So we could start with the standard model, and we could say, suppose that I want to do calculations at low energy. In fact, let's just suppose I want to do calculations at energy Q, momentum transfer Q, much less than MWC. If I'm relegating myself to low enough energies, I can actually ignore the W boson part of the story and just work with this simpler description. This procedure of removing these high energy degrees of freedom, notice the W is by far the biggest thing in this story because the quarks and the leptons are all trivial in mass compared to the mass of the W. So what you're doing when you go from here to here is you're basically removing the highest energy degree of freedom from the theory. This is called integrating out degrees of freedom. So typically we have a complicated microscopic fundamental description, and as we flow to lower energies, we are able to integrate out the high energy modes because they just don't play an important role, and that allows us to often describe the low energy physics with a simpler type theory. This is actually a much simpler thing to calculate with than this. Saw many haikus about hating on the weak interactions. You guys hated it, okay? Now, in the context of the Fermi 4-point interaction and the weak ultraviolet completion, this was a field theory and a field theory. So a field theory would flow at low energies to another field theory with a seemingly modified interaction. Okay? But renormalization doesn't have to connect field theories to field theories. So for example, you could imagine an atomic system that's just described by good old non-relativistic quantum mechanics, a crystal lattice or something. And if you look at length scales, which are large enough, a lot of times you can write down an approximate description in terms of some continuum theory. And a lot of times when you write down continuum limits of things, they take the form of field theories. Now, if this is a quantum system, then a lot of times that goes over to a quantum continuum field theory. But here's the thing. In this scenario, you would expect the field theory you get to be what? Non-renormalizable. Because you don't expect this description to be good at arbitrarily high energies or small distances. In fact, you know when it's going to break down. It's going to break down when your distance scale is of the order of the atomic spacing. If you're probing energies that high or distances that small, you can't use the continuum approximation. This is renormalization. Okay. So this brings us back to what we mentioned at the very beginning of class. And that is the problem child of perturbative quantum gravity. So perturbative quantum gravity, and I have to stress when I say this, I mean a very sort of narrow set of ideas. It's literally just trying to take general relativity but work with it in exactly a manner analogous to what we do with the standard model. There's a lot more in general relativity than that. Okay. If this is non-renormalizable, then we expect some ultraviolet completion. Well, the first thing we can ask ourselves is, at what scale do we think that ultraviolet completion is actually going to become essential? Okay. You know, the problem here is this is non-renormalizable, so we can't take momentum values q to infinity, because you get infinite results that you can't fix. So there's going to be some limit. You're going to go up to some value, but is there any sense in what that value might be? And the good news is that the theory actually predicts what that value is going to be. Because this theory is really built out of a set of fundamental constants. And from those constants, you can form exactly one combination that corresponds to a basic fundamental unit of mass. That's called the Planck mass. So the fundamental constants in question are, of course, Planck's constant, the speed of light, and Newton's gravitational constant, g. That's the only thing that appears in gravity. In Einstein gravity as well. Okay, in general relativity. You plug in the numbers, you get 10 to the minus 8 kilograms, which might not seem particularly big, right? I weigh a lot more than 10 to the minus 8 kilograms, but I'm on a diet. I'm going to get there one day. That might seem big, but you guys have to remember, when we look at total masses, we have to remember that we're not talking about macroscopic objects. We're actually thinking of the relevant mass is sort of, this would be the mass of a fundamental fluctuation of the theory. So literally this would be like a particle with this mass. Now to give you an idea of what this mass is, let's look at the masses of the biggest things in the standard model. Turns out that the mass of the W, plus minus, the Z, and the Higgs are all in the same order of magnitude. And these are sitting right around 10 to the minus 28. So this is actually a ginormous mass. Whatever fluctuation, whatever particle you encounter that has this mass, you better run. It's big. Let alone a macroscopic collection of these. Okay? If you want to convert this to energy scales, the Planck energy scale is, you could just multiply this times c squared, and this is 10 to the 19 GeV. And the Planck length, if you want to turn this around into a length scale, is right at 10 to the minus 35 meters. So clearly the problem of whatever is going to replace gravity, its ultraviolet completion, is something that we only have to worry about at extraordinarily small length scales, or extraordinarily high energy scales. We're not going to build colliders to probe these energy scales, ever, or probe these distance scales. In fact, in physics, there's really only two environments where these are really appropriate.
Black holes and your dreams.
Close.
That was the same thing.
Right.
Black holes in the Big Bang. Okay. Clearly, if you have a curvature singularity and you've taken any macroscopic amount of mass and collapsed it to a point, then the energy scale you're dealing with is as high as it needs to be. And then if you take instead the entire universe and collapse it to a point, the energy scale is plenty high enough. Okay, so the idea is simply that if you're ever going to have a theory which is going to accurately describe these environments, it's going to have to be the theory that replaces perturbative quantum gravity. Now, what might that theory be? Well, there are two candidates. I want to be fair. There are two candidates for the ultraviolet completion of perturbative quantum gravity. There's this one, which I won't say much about. And then there's this one.
Compensated.
Okay. Now, so seriously, loop quantum gravity, I have just in tiny steps tried to start looking at loop quantum gravity, and it's a very complicated, it's funny that people say string theory is so hard because I think loop quantum gravity is really difficult. But I'll just say a few words about these and then we're done. The very big difference between these two theories, among others, is that this is actually just a program that starts with general relativity and just tries to quantize that in a particularly savvy way. Okay? It's not doing perturbative quantum gravity, it's actually taking general relativity itself, the full theory, and quantizing it. And if you do it in the right way, it turns out you can end up with a theory that doesn't have these infinities. Okay, so it's not so much renormalizable as it is finite. Okay? However, when you do loop quantum gravity, that's all you get. You get a quantum theory of gravity. Everything else in physics is just still the same. Okay? So again, this is based on trying to quantize gravity. String theory is not that at all. String theory wasn't even trying to quantize gravity. String theory just says, I'm going to take this and replace it by this or this. What was discovered, though, was that in the process of doing that, we got a finite theory of quantum gravity. It was just kind of a miracle, but the reason that it's finite is actually almost self-evident. If we want to have problems with infinite energy, what length scales do we have to go to? Don't leave your jacket, it's raining outside.
Yeah. Oh, I'll shake your hand too. Great class, thank you.
I hope that hat didn't get on camera. Okay. Did anyone notice this hat?
What was the hat?
Oh, you guys have to see the hat later. I'm not even going to say. Anyway, so why might you expect this theory to be finite? Just looking at the picture.
It's closed.
Oh, no way. We've got rid of the infinitesimal size.
Yeah, so with points, it's meaningful to go to an arbitrarily small length scale. In string theory, there's a cutoff for how small you should ever think of something. You have to remember, these are fundamental. There is no physical sense in which you go, I wonder what this part of the string looks like. That's not part of string theory. If that was part of the theory, this wouldn't be fundamental. It would be a composite thing. The premise of string theory is that this whole object is fundamental, but this whole object has a non-zero size. So when you talk about length scales, you're never allowed to go to 0. You're allowed to go down to the string length, and that's it. And that renders the theory finite. Okay? But it gets better than that. Because it turns out that with string theory, you don't just get finite gravity, you get supersymmetry. Now, why do we care about supersymmetry? Well, there's a lot of things that supersymmetry does, but one of the really cool things about supersymmetry, which some of you know about, some of you don't, is the following. Remember how I said that coupling constants change with energy scale? If we actually look at the couplings in the standard model, we notice that those coupling constants run like the following. Okay? So this is just the way the standard model couplings for the 3 fundamental interactions vary with energy scale. And it turns out that this point right here is exactly the point of electroweak unification. Because at the electroweak unification scale, the electromagnetic and the weak interactions become one, but that means there should only be one coupling for them. So really the way that we should read this is that these come together, and then that line gets replaced by some single line, which is electroweak theory. Okay? However, if we add supersymmetry to the picture, then what we find is a picture that looks like this. And we actually find that if we take the standard model and we add supersymmetry to it, all 3 of the fundamental couplings of the weak electromagnetic and strong interactions come together at a single point, which tells us that at that point, there was really only one fundamental interaction called a gut, a grand unified theory. Okay. Which has been sort of an idea of theorists for a long time. Like, why is the standard model so ugly? Well, part of it's because there's 3 factors, SU3 cross SU2 cross U1. And if somehow there was only one factor, there would be only one interaction. Talk about the idea of unification. Like one interaction! Save them all! Okay? And Susie is sort of naturally pointing us towards that, and it comes for free with string theory. But it gets even better than that. Because if you're going to take SU3 cross SU2 cross U1 and make it a single interaction, what do you need? You need what, a Higgs boson?
Yeah, no.
Well, that's obviously a very important part of the story, because the reason we don't see this single interaction is because of some spontaneous symmetry breaking. But if this is all going to be part of one big interaction, what do you need? You need a big group. You need a gauge group which is big enough to hold all of this. Because remember, when we break symmetries, what are we doing? We're taking the group with some generators and we're giving some of them mass and some of them are remaining massless. So in electroweak symmetry breaking, we actually take this, which has 4 generators, and we break it to this. Sorry, this is U1 hypercharge. And we break it to electromagnetism, which has 1 generator. Okay? Of course, this group fits in this group. This is a bigger group. It can accommodate it. So if you want all of these, the 8 generators here and the 4 generators here, to sit inside of a single big group, it's got to be a big group. But guess what string theory has?
Big group.
It's got big-ass groups. It's got SO32. It's got E8 cross E8. Don't even ask me what the hell E8 is. Okay? These are groups with 496 generators.
Why?
I can't even write it. It's so mind-blowing. My ability to write has been paralyzed. Clearly, enough generators to accommodate the lowly 12 that we need for the standard model. Okay? So when some people ask me why string theory versus loop quantum gravity, there's a lot going for string theory. That and the fact that this is just like the simple stuff, like the whacked out stuff you see in string theory, extra dimensions, D-branes, orbifolds, orientifolds, M theory, F theory, No MF theory. There is F theory. There isn't. Anyway, in ADS-CFT, it's all really beautiful. But anyway, so that's where we're going to stop today and with the course. And yeah, hope you all have as much fun as I do.
We all shake your hand?
You're all smiles and acting nice now, but after reading some of those haikus, I feel horrible, like I've been putting you through the torture chamber.
That's pretty joke, tell it's fine.
So in string theory, black hole is like a finite size.